So one more piece remains in terms of closing out the controls on atmospheric and oceanic carbon dioxide levels through Earth history and evolution of carbon cycle, and that is magnetism and degassing, where degassing is basically where the CO2 is being forced out by, let's say, plate tectonic activities. Outgassing is, for example, what's being belched out from a volcano, or when you upwell cold carbon-rich waters close to the surface, the PCO2, partial pressure of CO2 from between the atmosphere and the surface waters, can drive outgassing, as happens in the Eastern Pacific Ocean, for example, where there is upwelling and the cold tongue. Over time, obviously, the continents have moved, as you well know. There is Pangaea 250 million years ago. There is Laurasia and Gondwana land 200 million years ago. Jurassic configuration by the Cretaceous, when the meteorite crash happened and dinosaurs went extinct. The modern continents were becoming visible, even though Australia is still down here. India was still south of the equator. And this is the present day. The continents are still moving northward, and in tens of millions of years they will all congregate towards the North Pole, and then the whole show starts again drifting southward. They are just floating on top of the mantle. So the idea is that these kind of plate tectonics obviously affects magnetism and degassing. Just briefly, for example, Indian subcontinent is here at this time. So you have to find a rock which has magnetic lines which show the latitudinal position. When a rock is at higher latitudes, the angle of the magnetic lines is much higher than when it's at low latitudes. You look at the way lines connect the north and south pole of the magnet and you'll understand. And then you need to time it. So at what latitude was it at what time? So you use other isotopes, uranium, lead, whatever else, the long ones, to date it. So you have to say at 250 million years ago it was at this latitude, and then it kept moving northward, etc. But here the other thing to remember is that as the continental configurations change, the equator to pole temperature gradient would change, atmospheric circulation would change, ocean circulation would change, shelf areas would change, species evolution would change. Remember, the plants were already, vegetation was already evolved, and we will see that marine species which could produce calcium carbonate in large amounts evolved much later, and that is shown here. So magnetism is going to affect degassing, but along the way life and biological pump would change the so-called carbonate pump as well, which would change, of course, the carbon sequestration and hence atmospheric and oceanic PCO2. This is a figure from this paper talking about the Mesozoic carbonate factory. So we are going here from 600 million years ago to the Cambrian, which started 540 million years ago, through the Paleozoic into Mesozoic and Cenozoic. You can see the non-calcium carbonate forming phytoplankton are shown here. So dinoflagellates, acritacs, diatoms, which are silica shells. The dinoflagellates don't have hard material, they dissolve and disappear, but there are other evidences that can be used to estimate their presence here. And Coccolithophores and Globigerina, the foraminifera, are calcium carbonate forming shells. They form shells of calcium carbonate, which would affect the carbonate factory. together with the continental configuration change and the climate change and the ocean circulation change, especially the shelf area change. Okay, so this is the percentage occurrence of the species. You can see that there was a jump during the Mesozoic of the calcium carbonate forming species, which is argued to affect, there was another jump here, it's argued to affect the area of calcium carbonate accumulation. Okay, so here Neritic deposition dominant, which means there was lots of shelf area available in the tidal ranges where the calcium compensation depth would have been very shallow, water column would have been very shallow, and you would have deposited large amounts of calcium carbonate. And then after this transition here, you see this drop in the area of calcium carbonate accumulation in million square kilometers. So this is kind of an indirect effect on the calcium carbonate pump and the atmospheric CO2 levels, which would have affected weathering rates, etc. But it is part of the estimate of CO2 along the way, so it is confounding the degassing that has gone on along the way. Okay, and we talked about whether vegetation evolution on land affected the weathering rates or whether they had much more impact on the silicate weathering feedbacks through CO2 temperature and precipitation. I have somebody ringing the doorbell. I have to pause here, sorry. Okay, this is the problem of recording at home. Coming back to this, we are looking at the indirect effects of vegetation now. So this is showing, going back to here 550 million years ago, so just to the end of Proterozoic and beginning of the Cambrian. You can see that the carbon burial amounts have changed along the way in terms of 10 to the 18 moles per million years, and there are also estimates of atmospheric oxygen and carbon dioxide along the way. Obviously, there have been very high amounts of carbon dioxide in the atmosphere before, as we know, and vegetation evolution along the way is shown here in terms of origination of rate in terms of families per million years and number of families, along with some species mentioned here in terms of forests, seed-bearing plants, flower-bearing plants, and so on. But the most important thing that this paper points out is that the Paleozoic landscape, fluvial and landscape developments were heavily affected by vegetation. So that would affect, so amount of rain would have been affected because of vegetation, evapotranspiration, boundary layer changes, and so on, surface roughness changes. But more importantly, just the weathering, erosion, and transport of material into the oceans would have changed as well. So the argument here is that climate regulation happened by vegetation evolution indirectly through the landscape evolution. So this is a different point than what we made before. Finally, to look at the impact of magnetism itself, here we are looking at cumulative proportion of young grains compared to the mean age of young grains, configuration of continents, ice house, greenhouse intervals, and modeled Phanerozoic CO2 levels. So we are going here from 800 million years ago to the present Paleogene, Neogene. We are looking at continental configurations in terms of rodinia breakup, dispersal of plates, assembly again to have Pangea, then Pangea breaking up, and dispersal again, coming to the recent events of alpine and Himalayan collisions. So we talked about weathering rates being affected by these events, but there was also flood basalts and so on. So magnetism and degassing would have been affected as well. These are the age estimates based on zircon, which I won't bother with. They are using different windows here. Average cumulative proportion of young ages within 200 million years of minimum depositional ages and 300 million years window, so slightly different proportions of zircon. So basically these zircon, uranium, lead age is used to estimate magnetism. Very large uncertainties, as you can see here. But the main point is that these obviously affected degassing rates and CO2 levels. So when you had high CO2 levels, you had greenhouse effect, very warm climates, and as CO2 dropped off, we got into these late Paleozoic ice house, then the Mesozoic, early Cenozoic greenhouses, and then the Cenozoic ice house. And the earlier cryogenic ice house in the Marinoan and Sturtian are not related to the not directly interpreted here in terms of the CO2 levels, because the zircon proportion and so on, they don't allow us to relate the CO2 levels to these glaciations. Some uncertainty remains. Okay, so that's the degassing story, which should bring us fairly close to the end of evolution of the carbon cycle. We'll revisit the reverse weathering in a minute through Earth's history in terms of its control on carbon cycle and climate regulation, and then we will compare carbon cycle to other geochemical cycles like sulfur, oxygen, and so on, because they are all related in terms of the evolution of carbon cycle through evolution of species, for example. And that should bring us to the end of this Earth history in terms of evolution of carbon cycle and climate regulation. Okay.